Hey, this is an overview of the algebra and geometry of vectors. A vector is an ordered set of numbers. Here's an example right here. There are three ordered numbers, 2, 5, and 2, and I've enclosed them in round brackets. I'm going to actually call this guy Q, and so sometimes I'll write the Q right before it, and then the coordinates of Q. Now, this has three components, so it can be regarded as a point in three-dimensional space. And indeed, here's a representation of free space, and there's the point right there. Its x-coordinate is 2, its y-coordinate is 5, and its z-coordinate is 2. Well, let's see, what does that mean? Its x-coordinate is 5, which means if I project it orthogonally, its y-coordinate is 5. If I project it orthogonally onto the y-axis, it projects onto 5. Here's another vector P. Its coordinates are 1, 2, and 3. And so its y-coordinate is 2, so it projects to 2. And so on the z-axis, this one projects to 3. And this guy projects to 2, and so forth. So the point here is there's lots of ways to write this vector. Sometimes I'll use square brackets instead of round brackets. When I'm doing that, I'll often do it to get me to think not of the point so much, but of the arrow joining the point to the origin. And so here's the arrow for Q, here's the arrow for P, and when I'm writing this, I'll often use a small boldface letter rather than a large letter. So there's Q, and so I might write it here, Q, and I might underline it to get the boldface. There's P, and I'm thinking of the arrow. I might also write it as OQ. This is the origin. It's often called O, and OQ makes me think of the arrow from O to Q. Sometimes also I'll write it as a column vector. This is a row vector. I'm still using square brackets, but I'm going to write it as a column. How I write it will depend on what I want to do with it. And we'll see a lot of that pretty soon. Okay, well, what am I going to do with these vectors? I'm going to do algebra with them. And so here's some algebraic things that I can do. I'll multiply them by scalars. So there's my P. 3P is just got by multiplying all the components by 3. It's got a geometric representation too. There's P right there. 3P is, its vector is in the same direction as P, and it's 3 times as long. So this is the point 3, 6, 9. Here's Q, 2, 5, 2, minus Q. I'm multiplying this by the scalar minus 1. It just multiplies all the components by minus 1, and it goes in the opposite direction and is the same. And say 1/2 Q, that would be that point right there, and there's the vector 1/2 Q. Okay, I can also add them. So the sum of P and Q, there they are there, is the vector R, and you just get it by adding the components. Actually, I've written these, I've chosen to write these as column vectors because then it's really easy to see the sums coming across. Now there's a very nice geometric representation of addition. Over here there's Q, there's P, now, and R is got the product by sum by forming a parallelogram with P and Q. So this is parallel to P. In fact, this is kind of the vector P just moved over so that its tail is over here at the head of Q, and you get R that way. Or you can take the Q vector and you move it over so its tail is at the head of P. So there's a copy of the Q vector. Either way, if you do them both, you get a parallelogram, and that's R up there. And you can see why does, for example, does R have y coordinate 7? Well, Q had y-coordinate 5, remember that, and P had y-coordinate 2, and so that means that distance there will be 2, because it's the same as that distance, and so that's at 7. 5 plus 2 is 7. So the parallelogram law works. Well, if we put scalar multiples and addition together, we get what are called linear combinations. So here is a linear combination of P and Q, the sum of scalar multiples. And here's in fact what it comes out to be algebraically. These are the components, the corresponding combination of the components of P and Q. Now, since we have nice geometric representations of scalar multiplication and addition, we have a lovely geometric representation of linear combination. And to do that, it turns out that all the linear combinations of P and Q are going to lie in the plane spanned by P and Q. So I'm going to take that plane in 3 space and just focus on it. And in order to make a clean picture, I'm going to get rid of everything in 3 space, the axes and so forth, except for the P and the Q. So that gives me this picture down here. I'm still in 3 space, and this is the plane spanned by P and Q. And now what I've done with this plane is I've drawn a lattice structure determined by the vectors P and Q. And so now actually you can see all the linear combinations. Well, we've seen this before. This is the sum. And we've seen this before. That's 3P. Okay, so there's 3P. There's P plus Q. Well, away you go. This is 3P plus Q, right there. And this is 2P plus 2Q. No, this is P. 2P plus Q. Right? 2P plus Q. And there's minus Q. And here's minus P. And so what you can see is that the lattice points are all the linear combinations where A and B are integers. So those are the integral linear combinations, but now if A and B are real numbers, the linear combination is also on this plane, and that's illustrated by this fine structure that we've got in here. Here I've actually made a subgrid, 5 along each edge, and so these are fifths, and so W is in this little box here, and it's 3/5 over and 2/5 up. So what is it? W is in fact how many P's? 1 P and then 2/5. So it's 1.4 P. And how many Q's? 1 Q, 2 Q's, and then 3/5, which is 0.6, so it's 2.6 Q. So that's W. And so now actually that should convince you that if you have any real numbers A and B, the corresponding point is going to be determined proportionately in this grid structure. And in fact, the result I want you to get out of this, and this is quite a significant result, all the linear combinations of P and Q for any A and B lie in this plane. And for any point in the plane, there's only one way to write it as a linear combination. Any point in the plane, we do the subdivision up. We see how far it is along in this way and how far it is up, and that determines the A and the B. So there is a one-to-one correspondence between the points of this plane and the linear combinations of P and Q. That's kind of the theorem. Okay, well, these are linear combinations of 2 vectors. I can do the same thing with 3 vectors. All right, there's 3 vectors. I've got my P and my Q, and I'm going to add a new vector R. 3 vectors in 3 space. Now, R is not in the plane spanned by P and Q. It's the plane we had before. If R was in here, I wouldn't ever get out of this plane by adding R. So I've got this R which is not in the plane. And, well, before I had the plane, and I had the lattice structure in the plane. Well, now I'm going to fill 3 space, and my lattice units are actually boxes, and they're down here. So instead of those lattice parallelograms, I have boxes. And now the picture is a lot harder to draw. I'm not going to actually do a lattice structure of 3 space using these boxes. So you'll have to imagine just how that works. But the same thing is true. We do the same kind of thing we did before, including the line structure of W. Every point in 3 space, now this is the result that's important, every point in 3 space can be written as a linear combination of P, Q, and R in a unique way. So this is kind of the theorem about linear combinations. If I have 2 vectors P and Q that are not multiples of one another, if they lay along the same line, you wouldn't get the plane out of them. So here's this, that's this case right here. They span a plane, and every vector in the plane is uniquely a linear combination of the two of them. And if I have 3 vectors P, Q, and R, and they do not all lie in the same plane, so they form a box, then every vector in R3 can be written in a unique way as a linear combination of P and Q. We're going to use that theorem quite often, and I think it's geometrically clear once you've got the picture.